On and watched the video for the test, and now we're going to do a little catch up on our lesson today. So the first thing I want to talk about is our agenda. So what I've done is here's my agenda, and my agenda will show you what you should have in. I think I'm missing one thing, which I think that is the test. We did an online test on that day. I'm going to put that down, and then I'm going to go ahead and turn to where I am today. So on this assignment, the first one was kind of lengthy, so I want to kind of go over that with you, which is over here. So if you're looking in your textbook, we're going to be on page number 236 to 243. So what it does first is it talks about a baseball player and how the second law, action-reaction forces, and how it changes the ball's velocity. So what it's doing here is it's giving you a definition of an impulse and what an impulse is. And it tells us an impulse, and we would use that equation that is listed there in front of you. F change in t equals m times vf minus v initial. And so, I'm sorry, I'm starting my timer so I don't run over. And so then what they do there is they were just telling you that the definition of what an impulse is. And I'm sorry, I was looking at something else. What an impulse is, which is a product of an average force of an object in the interval over which it acts. So it showed you a force and a time, and it was talking to you that the force varies with the time magnitude of an impulse area under this curve. Okay. Then it actually introduced you to momentum, and it talked about momentum equals mass times velocity. And when we do that there, we also can plug it into this, and it would extend that over a little bit more. So the impulse momentum theory is where we're having our F times change in t, which is my impulse, times my final momentum, subtract my initial momentum. And the units is 1 Newton is equal to 1 kilogram times meters per second. PF, which is our impulse theorem, is PI plus F change in T, or we can also change this formula to VF equals PF divided by M. So these two are two variations of that. And so, sorry, on my next page, it gave you some sample problems, and that's where we are right now. So the sample problems that I have, the first one says a compact car has a mass of 725 kilograms and is moving at 115 kilometers per hour, and it's moving toward the west. Sketch the moving car. So here's my sketch of a moving car. Find the magnitude and direction of momentum. So for that, I'm taking the 725, I'm timesing 115 kilometers, and then I need to change it to seconds, meters per second. So in my calculator, if I am doing this, the first thing I'm going to do is I want to change it. I'll keep it in scientific. We're all good. So then I'm going to do 7.25, open bracket, close bracket, open bracket, 115, close bracket, and then I'm going to open bracket, but this time I'm doing alpha y enter, which I'm going to do my 1000 over my 1, and I'm going to close my bracket, open my bracket, again, alpha y enter. I'm going to do 1, and then down, and that would be 3600 over, close my bracket, and I got 2.31597, and I changed it to 3.32 times 10 to the 4th power. So then the next one that we have here is we're looking for B, and B is the second car, has a mass of 2175 with the same momentum, what is the velocity? So this one, we're going to do our alpha y inner. We're going to do our 2.3 times 10 caret 4 over. I need to delete that. Close bracket, open bracket. And I'm going to do this linear because it's on top this time. 3600 divided by 1, close bracket, open bracket, 1 divided by 1000, close bracket. And then I'm going to go down here to the bottom and put 2175. And if I hit enter, I get 3.84. And that's where we're rounding it up to. Okay, so now what I'm going to do is I'm going to go on to my second problem. It says a driver in a compact car is previously steadily applying his brakes at 2.0 seconds. As a result, the average force is 5.0 times 10 to the third Newton exerted on the car to slow down. What is the change of momentum? Or equivalently, the magnitude of the direction of the impulse of the car. So, my force is a negative because he's stopping 5.0 times 10 to the third. And the time, it tells us it's 2 seconds. So the only thing we're going to do here is we're just going to take that number times that number to get this one. And for B, it's complete before and after sketches. Determine the momentum of the velocity of the car now. Here's the velocity, here's the before, and then the ending. And so then what I'm going to do here is I'm going to do this formula here. And so I'm trying to find PF. So I'm going to take my force of change in time, plus I'm going to add my P1, and I get 1.3 times 10 to the fourth kilograms per meter as it goes easterly. So now what I'm going to do is I'm going to now go on to page 239. So page 239 continues, and it talks about the impulse momentum theory, and it's telling you how we're going to now have it with a car and car crashes. So when cars are, people are dying, they decided to use this impulse theory to figure out the airbag and how to fix that. That's how it saves lives. On page 240, it talks about angular momentum. Rotating objects' angular impulse is this. And this is, of course, the I, which is WF minus WI, and the change, that's the change in W. Okay? So then we're going to do angular momentum, represented by I, and a moment of inertia is is L. That is I, and then the object's angular velocity is that funny looking W. The angular momentum is kilograms times meters per second squared. Angular impulse angle momentum theory has to do with angle impulse object, final angular momentum, and you're subtracting the object's inertia's angular momentum. And so here it also talked about object's angular velocity can change, the shape of the object changes. And then it talks about some examples about a pool and some examples from an ice skater. If you want to look at those, that's fine. Then it gives us the question of our example problem, so I wrote that down. And then you had to do 6 and 8 on page 243. So on 6 it says a 0.25 meter diameter circular saw in a workshop rotates at 5.0 times 10 to the third RPM shown in figure 7. After the electric power of the saw is turned off, it takes several seconds for the blade to slow down to a complete stop. The momentum of inertia of the blade is 8.0 times 10 to the negative 3 kilometers per meter square. Friction of the axle provided on the angular torque is 2.3 times 10 to the negative 1 newtons per meter to slow the blade. How many seconds does it take to stop the blade? So what you're going to do here is you're going to use this equation here, where you're going to take your negative 524 rads per second times it by your 8.0 times 10 to the negative 3, and then you're going to divide that by your torque. So that is alpha y, enter. So then I'm going to do a negative 524, 8.0 times 10 to the caret of a negative 3 over down. Whoop. Let me go back up and close that bracket. And then I'm going to have a negative 2.3 times 10 caret negative 1 over, enter. And I get 1.8, I get 1.8226 E1, and if I want, that would be a correct answer. And if I wanted to change that to a normal mode, I could, and that gives me my 18 seconds. So the next one that we do for number 8 says a bowler releases a ball into an alley. The ball does not roll on its back but slides. Slowly, the friction of the alley's surface causes the ball to roll, and then finally angle velocity of 7.0 times 10 to the negative 1 rads. And the momentum of inertia, the ball at 0.350 kilometers per meter per second. The ball moves down the alley at 2.4 seconds. What is the angular impulse? So, for angular impulse, I'm going to use this equation here, which is going to be my 2.45 divided by 2.4 seconds, which gives me 1.02. Okay, so I'm a little bit slow today. I am at least another video short. I'm getting ready to leave to go to lunch, and then I'll be back and I'll post the other one. I'm going to go ahead and change the assignment so that you can see this video, and then after that I will go back in and change it for the next time. I hope you have a blessed